Hi, welcome to Modern Optimization Methods. Today we will introduce the third part of Chapter 6, the support vector machine. Now, let's start with the illustration of support vector machine. Support vector machine is divided into support vector classification and support vector regression. For example, we take support vector classification as an example. It is trying to separate two types of data by a hyperplane. Okay? So in two-dimensional space, we are trying to find a line to separate the two sets or two types of data. So the aim is that we try to make the distance between the two sets as far as possible. This is support vector classification. And the vector which lies on the boundary of the two lines here, they are called support point or support vector. And for support vector regression, the aim is similar, which is we try to find a hyperplane or a line in two-dimensional space such that the points will lie around the line as close as possible. Okay, so these are support vector classification and support vector regression. Now, mathematically speaking, the support vector classification are given as follows. We have some training data called x1 until xl in n-dimensional space. So n can be viewed as the number of features. And we have the corresponding labels y1 until yl. Okay, for example, for the data x1, it is label 1, or for the data x2, its label y2 is -1. All right, so just identifying different types of data. Then support vector classification is looking for a hyperplane omega transpose x plus b equals 0. Here, the omega is what we want as well as the b. Okay, so we are looking for a pair of omega and b such that the resulting hyperplane can separate the two types of data as much as possible. So putting it in mathematical form, we actually try to maximize the distance between the two types of data such that all the different types of data can be lies separately or lies strictly on the different sides of this hyperplane. And since the distance can transfer into the square of omega, then we minimize the norm of omega such that the following inequality holds. So the inequality basically says that if the data is positive data, then all the positive data lies on the same side of a hyperplane, and the other negative data will lies on another side of this hyperplane, okay? Meaning that the two types of data are separated strictly. However, in practice, the data may coincide or may mix with each other, and we cannot separate them strictly. So in this case, people bring loss function into the model, and they try to solve the model like this. So we got still minimizing the norm of omega such that we also have a loss function, okay? So such loss function actually measures that how much you have misclassified the data, okay? So we have different ways of loss function. For example, the L2 loss function basically takes the following form, that if you are mixed labeled or misclassified, then we take the square of the misclassification and put it into the penalty term, or we penalize the loss. Okay, we try to minimize the loss as well. So this is the resulting L2 loss SVC model. And this is actually the main model we are interested in. Now, for support vector regression, the mathematical statements are similar, and we have training data x1 until xn, and we also have some observations y1 until yl. Here, L is actually the number of samples. However, different from classification, the observation y1 to yl here are real values, which may be positive or negative or very large or very small, okay? So we try to find a hyperplane omega transpose xi plus b such that the data will lie as close as possible to this hyperplane, okay? So this is the mathematical form for the regression problem. However, as we mentioned before, sometimes the data cannot be lies strictly within the area, so we bring the loss function into the SVR model, and this is one way of the L2 loss SVR model called epsilon L2 loss SVR. So the SVR and SVC, the two models, are what we are going to focus on in this part. Now, let's take a look at the traditional formulation for SVC. We take SVC as example. So the traditional way to formulate the L2 loss SVC model is like this. We introduce a variable C to represent the loss. And then we put the loss as constraint, okay? So we require that this loss to be non-negative, and also it is greater than the condition here. And notice that this is also referred to as the prime form of SVC model, okay? So in this optimization problem, if we count the variables and number of constraints, we can see that omega, C, and B are the variables with dimensions n, l, and 1, okay? And the number of constraints is actually double size of the sample size, okay, 2L. So this may bring some potential difficulties. If you got large size of samples, meaning that L is very large, then the constraints there will be a lot of constraints. And of course, the variables also involves the number of constraints, C, right? So the problem will have a large size and large number of constraints. If we take a look at the do problem, okay, here we ignore how we derive the do problem. We put this part into chapter 7, all right? And we present the do problem here, actually. So the do problem is like maximize a quadratic function subject to some equality constraints and box constraints, okay? So if we take a look at the do problem and we count the number of variables as well as the constraints, we can see that the number of variables alpha is the same as the number of samples L. And the number of constraints here is a box constraint as well as a one equality constraint, okay? So in other words, if you got large number of sample size, then this problem will got very huge scale in terms of variables. All right? Now, actually, there are many existing literatures trying to solve the SVC problem. Here, I listed some of them, and the most popular one is the coordinate descent method for primal problem, as well as the do coordinate descent method for do problem. We use the DCD to stand for the do coordinate descent method for the do problem. And another famous one is the trust region Newton method. We use the tron to represent the name of this method. Okay? And for the L2 loss SVR, there are also some existing works. For example, the tron and the DCD applied to SVC model, as well as a recent work, a smoothing Newton's method for the primal problem. In terms of state-of-art softwares, the most popular software for SVM is the LibLinear and LibSVM, the two softwares. And you can see here I list the web page for LibLinear method that you can search on Google and download the software there. For LibLinear, it is actually designed for linear SVM. And for LibSVM, it is capable of kernel methods. Okay, so the two packages have some difference. And as we mentioned before, the tron and DCD, they are incorporated in the softwares, and you can use them to compare with your methods. Okay, so actually, when we propose the semi-smooth Newton's method to solve SVR and SVC, we can compare with tron and DCD in this software. Okay, let's make a brief summary about SVM. In this part, we introduce the preliminary knowledge about SVM, basically including SVC and SVR. We also include the mathematical models for the two problems, as well as some state-of-art softwares. In the next part, we will introduce how we apply semi-smooth Newton's method to solve the SVM problems. Okay, see you next time.